about piecewise defined functions or piecewise functions first this evening. And piecewise functions are exactly what that first word says, pieces. So they're made up of different parts of other functions, and they are put together on one graph is basically what happens. So there's multiple pieces with specific domains. And what do we know about domain from 100 or just in general? That's the x values. It's going to tell us what x values this piece works for, and then what other values that it works for. So again, remember domain, just like you said, is x, and then the range is y. So as we're looking at these piecewise defined functions, we're going to graph them. We're also going to talk about the domain and the range. And then there's a thing that we're going to talk about called continuity. And that's one of those concepts that's probably best explained once I get one drawn, what continuity is, because it's a really simple concept, but it's really hard to put into words, but it's really easy to see. So let's just start with our first example. F of x is equal to, and then we do this little curly brace thing like that. And the first piece is going to be negative 3x plus 4 if x is less than or equal to negative 1. The second piece, and this one's only going to have two pieces, is going to be x plus 5 if x is greater than negative 1. So the domain pieces that we spoke about earlier, the specific domains for each piece. So this piece, it looks like that only when x is less than or equal to negative 1. And so the domain for the top part is from negative infinity up to negative 1 on the x-axis. And then this piece takes over right after negative 1 because this domain says greater than negative 1. It doesn't say equal to, so it doesn't. This one doesn't include the negative 1, but it's everything after that that it includes. Okay, so when you're trying to graph these functions, one of the things that I like to, it makes it easier for me, and I think helps you understand it, is finding these what I call important points. And each piece is going to have at least one important point. Some of them, as we see as we go on here, are going to have more than one important point. But each of these has one important point. And that important point is where the x value is listed for the domain. So in this case, it's at negative 1. We need to know where is this graph at in terms of y when x is negative 1. So if I plug in negative 1 into that first function, that'd be negative 3 times negative 1 plus 4. And we get a y value out of that. So it'd be 3 plus 4 is 7. So the first important point for this first piece is at negative 1, positive 7. Okay? So what I'm going to do is I'm going to draw myself a little coordinate plane down here. X and Y axis. Just make sure, just about a 10 by 10 would be plenty. And I'm going to go to that important point, negative 1, 7. And at negative 1, 7, negative 1, 7, negative 1, 1, 2, 3, 4, 5, 6, 7. I'm going to put a filled-in dot. The reason I'm going to put a filled-in dot is because it has an equal to mark on the inequality. X is less than or equal to negative 1. So that means that that point counts. Okay? So I put the filled-in dot here. And then I'm going to look at the inequality. And it says x's are less than or equal to negative 1. So which direction is that going to go? To the left or to the right of that point? To the left, because it's less than, right? So like this is negative 2, negative 3, in that direction. Okay, so I want to follow this graph with those x values. Okay, what do we know about negative 3x plus 4 in terms of just it being itself? What kind of function is it? What's its graph look like? It is a line. It's a slope-intercept form of a line, negative 3x plus 4. The slope of that is what we want to use. We want to go down, we'll show a negative 3 slope. A negative slope should be going down and to the right. So it should look something like what my arm's doing there, right? So that would be up 3 and left 1. Up 3 and left 1. That thing follows that line. Okay. If I'm not sure what the graph looks like, I had to know that that was linear and it's going to follow that slope. I can just pick x values that are to the left of negative 1 and plug them in. If I pick negative 2, which is to the left of negative 1, and plug it into this problem, negative 3 times negative 2 be positive 6 plus 4 is 10. Look here at negative 2. 1, 2, 3, 5, 6, 7, 8, 9, 10. That's that point. So even if you don't know what the graph looks like, you can plug in x values and get the picture happening for you. So don't think, hey, I have to have all these functions memorized and what exactly they look like and all this stuff. Well, that's helpful and it speeds you up, but you can just plug in x values and get the picture going by just plotting points out of that. So keep that in mind as you're going. So we found that important point right here, and then we graphed the rest of that line. So we put an arrow on it because it's continuing that direction toward negative infinity for the x values. Now let's go to the second half there, that x plus 5, if x is greater than negative 1. It also has an important point at negative 1 because that's the number that's right there is a negative 1. So I'm going to find out what's going on there. So I'm going to plug in negative 1 plus 5, which would be 4. So it has an important point at negative 1, positive 4. So on my graph, I'm going to go to that point. I'm going to negative 1, positive 4. 1, 2, 3, 4. And on this one, I'm going to put an open circle. Why did I put an open circle on that one compared to putting a filled in dot on the other one? Yeah. The negative 1 doesn't go with it on the second half. It doesn't have the equal to mark there. So if it doesn't have the equal to mark, that's how I know to put an open circle. Equal to mark, filled in dot. No equal to mark, open circle. Okay. Now, it looks like x plus 5 for every x value that's bigger than negative 1. So I could either think, okay, this is a linear equation with a slope of 1, or I can plug in x values that are greater than negative 1. It doesn't matter which way I do that, I'm going to get the same picture. So if I follow the slope is 1, I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, and I draw that line. And that gets me my graph. 1 over 1, up 1 over 1. That is the picture of what I'm looking at as far as a piecewise defined function. Now, with that, let's talk about the domain. And we're also going to talk about the range. The domain you can actually get without having the graph. So if you get on a Canvas quiz and it only asks for a domain, you can actually get that. It tells you the domain right here in this part. It says all the x's that are less than or equal to negative 1. So where does that go? What x values are less than or equal to negative 1? Well, negative 2, negative 3, negative 4, negative 5. Keep going. Eventually, we're getting toward where? Negative infinity. Because it's going all the x values that are less than negative 1. The first piece uses negative 1. The second piece where does it start? Where's the domain start for the second piece? What was the first place we went to? -1. So -1 was used in the first piece, but it wasn't used in the second piece. But the key is that it was used. So we're not skipping -1. We're not skipping any numbers. There will be times when you may skip some numbers, and we have to take care of that. But this time we don't skip any. And then it says all the x's that are greater than -1. Well, where do we end up getting to when we go greater than -1? Infinity. So this one actually has a domain of all real numbers, or from -infinity to +infinity. All real numbers, though. Remember, those being the same thing. Okay? Now, the range, it's a little bit more difficult to get without the graph. If you've got the graph, the range is a lot easier, because all you've got to do is then read the graph from bottom to top. Reading that graph from bottom to top, what is the lowest y value that is shown there? 4. Is 4 included? No, because it is what kind of circle there on our graph? It's open, it's empty. So that 4 is not included, but that's the first place we marked when we read it from bottom to top. Then that red line, it's pointing, well, it's hard to see that it's red. That's red on my screen. It's not too good. This line is going up, right? Where's that going toward? +infinity. Where's this one going to? It's going up, ain't it? It's going to the same place. Maybe going a different direction with the x's, but it's still going up toward +infinity. So they're both going to end up at +infinity. The lowest number we have is 4. The highest is +infinity, because that line keeps going up forever. So our range is from 4 to +infinity. Now, told you we're going to talk about this thing called continuity. Continuity, the first part of that word, C-O-N-T-I-N-U, it's like the word continuous, right? Or continues. If something is continuous, what does that mean about it? It never stops, never takes a break, right? Continuous, it keeps going forever. Dude, when you're looking at a graph, is this one continuous if you try to use both pieces? Can I get from this one? Do I have to stop?
Yeah.
And then I got to jump to get to the next one, right? So if I have to stop and move, is that continuous? No. So this one is what we would call, the continuity for this one is what we would call discontinuous. Okay. The best way that I've ever found to explain this is that if you can trace the graph with your pencil, start the leftmost point you have and trace all the way across to the right on your graph, and you never have to pick up your pencil to move to another spot, it's continuous. If you have to stop and pick up your pencil to get to the next spot, that's discontinuous. So this one, if I'm trying to trace that, I got to stop right there, pick it up, and go here. That's discontinuous. If I could just go and never pick it up, that would be continuous. So the continuous ones are going to be connected to one another. That's what, continuous. It never stops. It keeps going, right? Connects together. So this one would be discontinuous. Excuse me. Anybody knows how to get rid of a cough you've had for 3 weeks? Not my thing. So let's try another one. Let's look at example B. Let's go back. Calculator. Let's do number 1 with the calculator. Forgot I was going to show you that. So get out your graphing calculator. Ooh. There we go. All right. So I'm going to graph each of those pieces. All right. So what I'm going to do is I'm going to go to y equals, and I'm going to clear everything out. So make sure yours is clear. Make sure you don't have one of those plot 1, 2, or 3. Make sure none of those are darkened in. If they are, press the up arrow. So if you got in there and your plot 2 is darkened in like that, you need to press the up arrow, go over to that and hit enter, and it'll turn it off so it won't mess up your graph. Now, on Y1, we're going to type that first piece in. So put parentheses, and this is part of the game as far as getting your calculator to do a piecewise defined function. It's a little tricky. All right, so got to do parentheses, and then I'm going to type in negative 3x plus 4. Close parentheses. Okay? So whatever your first piece of your function is, you need to put it in parentheses. Then, right beside it, don't hit a space, don't hit enter, don't hit anything. Open up another set of parentheses. And this is where we're going to put in our inequality. Okay? So we're going to get our calculator to put in x is less than or equal to -1. So I'm going to type a x, and then here's how you get an inequality symbol with your calculator. You're going to hit second math. And notice what comes up. It's the test menu, which is where the inequalities are coming. So we want less than or equal to, which is that last option, option 6 there. And then we type our number, -1. Close those parentheses. Press the up arrow. If it's blackened in like that, press the up arrow and get it blinking, and then just hit enter, and it should change its color. Did it? All right. All right, so I'll put in the first piece. I'm going to go ahead and type in the second piece, do the exact same thing, parentheses around the function. So parentheses, x plus 5, close parentheses, and open up another set of parentheses. And then we're going to put our inequality in there. It says x is greater than -1. So x, second math, greater than is the third option, -1. Excuse me. And then we're going to hit graph once we've done that. All right. This little blue piece up here, that's that first part that I drew. It's coloring in. If you've got the color version, you can see it. If you've got the black and white version, you may not see this. But it's actually coloring in the x values that are down here that are not getting used for the different colors. Because it's reading as 2 separate functions. We're kind of faking a piecewise defined function with a calculator. It's not really doing a piecewise defined function. It doesn't know that's what you're trying to do. So here's that first piece. Here's that second piece. The same picture we drew by hand. So we can see that happening there. We can see what's going on. We can see that graph, and we can do anything we needed to with that graph there. So we get a pretty nice picture. It's not the greatest of things, but it's kind of handy sometimes if all you've got to do is pick the right graph, which that's I've seen that on the final exam a couple of times where they just said, here's a piecewise defined function. Which one of these is the right graph? Well, you can graph it and find it. So it's doable. All right. Example B. G of x is equal to, and let's get a couple pieces here. Let's do -2x if x is less than -3, 3x minus 1 if -3 is less than or equal to x is less than or equal to 2. And then let's do a third piece on this one. -4x if x is greater than 2. So 3 pieces on this one. All right. Now, again, important points. Each one of these is going to have at least one. The second one's going to have 2 because the inequality has 2 numbers on it, right? So that's how you know where your important points are. They're going to be the numbers that are in the inequalities. So for the first piece, I'm going to find out what's going on at -3. So I'm going to plug -3 in for x to find that important point. So what is negative 2 times negative 3? Be positive 6, right? Okay. So when I go to graph that, I'm just drawing a generic coordinate plane here. I'm going to go to negative 3, positive 6. I put a filled in dot. Should it have been a filled in or not? No, it should be open, shouldn't it? Why is it open and not filled in? That's right. It's not equal to, so we can't have that. All right. Now, the next thing to do is get the rest of that graph for that piece. So negative 2x, I need all the x's that are less than negative 3, so that'd be like negative 4. If I plug in negative 4 for x, negative 2 times negative 4 is positive 8. So that's going to be up here. Notice that that follows the negative 2 slope, and that makes a straight line. So there's my first piece of my piecewise defined function. 1 down, 2 to go. Second one's a little bit more difficult because it has 2 points on the ends of the graph. So we just need to find the 2 important points. So negative 3, plug that in. So that'd be negative 9 minus 1 is negative 10. And then the other one is at 2. So plug that in. 6 minus 1 would be 5. And what does the graph of 3x minus 1 look like? What kind of shape is it? Straight line, curved line, you know, the parabolas that we did, or one of those cubics that we did that, you know, kind of did this number. What's it look like? Straight line. Yeah, it's a straight line. So the good news is, since it has 2 endpoints, all I've got to do is just connect those 2 dots, and I've got it. So are they going to be filled in dots or open circles for this one? Filled in, because they're both have the equal to mark. So I'm going to go to those points. Negative 3, negative 10. So negative 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Filled in dot. And then go to positive 2, 5. And then I'm going to connect those 2 with a straight line. I don't even have to count the slope or anything for that. That's nice. All right. Third piece. Let's get the important point for it. What's the x value for the important point for part 3? 2. Thank you. All right, plug that in. 2 times negative 4 be negative 8. So I'm just plugging in x values, getting the y value that goes with it. And I'm going to that point, 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And I messed up and put a filled in dot. It should be open because it doesn't have an equal to mark. And then the slope is negative 4 or any x value that's greater than 2. So I could plug in the 3 and get negative 12 if I wanted to. Go there. And or down 1, 2, 3, 4 over 1. And I miscounted 12. 1, 2, 3, 4 over 1. And that line goes down that direction. Okay. Now, this picture is kind of big. Got a lot, you know, it's going in different directions there. So we're going to talk about the domain and the range of this. Again, the domain you can get from the inequalities that are in the piecewise defined function. You don't have to get that by looking at the graph. The range, the graph is very important as far as getting that range. So it's definitely handy to have that graph. So Domain. I'm going to look at those inequalities. It says all x's that are less than -3. So that would start at -infinity. The first piece stops right when it gets to -3 and does not include -3. Does -3 get used in the next piece? Yes. So I don't skip it. So I'm still riding along the number line that is the x-axis. I've got to -3. I thought I was going to have to skip it, but I didn't because the next piece used it. So I'm going to still truck along, and I get to 2. And does this piece use a 2? The second piece. Yeah. Does the third piece use the 2? Look at the inequality. No, but the whole function did use the 2, right? That's the big idea here is the domain has to deal with the whole function, not just individual pieces. The individual pieces add together to get that domain. So we're not skipping any numbers here. Everybody that we thought might get skipped got used by one of the pieces. So our domain for this one is again -infinity to +infinity. Now, let's look at the range. Remember, how do you read range? From the bottom to the top. So from the bottom, what's the lowest y value in our problem? That's the lowest one we marked. But what does the blue piece, the arrow, tell us it's going toward? -infinity. So this one, yes, -10 was the lowest one point we marked, but this line keeps going here all the way to -infinity. So our range is going to start at -infinity. And then it follows the blue line until it gets to this little open circle. And then the green line, it covered up that spot, right? It used that same y value that this open circle represented, right? And then we would keep riding the green line or this middle line here, and it goes up to here and stops. What is that y value? 5. Does the other piece use the 5? If I go straight across there? No. Oh, so we've got a stopping place with our range. Our range stopped at 5. Was that 5 included in the range or not? And how can I tell? It's a closed circle, so it's a yes. It is included. Where's the next place that the range starts back up at? Over here. What's that y value? That'd be 6, right? Because 4 would be going down. We're reading bottom to top. Yeah. All right. So going to 6, is 6 included in this range? Why not? It's an open circle, so it's going to be a parenthesis. And then where does this first piece end up going? +infinity. So there's our range for that one. What about continuity? Discontinuous. Because we cannot trace it without picking up our discontinuous. There we go. My N's and U's look so much alike. I need to fix that somehow. Sorry about that. Okay. Discontinuous. All right. So let's graph this one with the calculator so we can see how to do one of those compound inequalities with the calculator. It can't handle it the way it's written. All right. So I got to show you how to do that. So graphing calculator, y equals, clear it out. Clearing out everything else I did for example A. Going to this one. So parentheses, first piece, -2x, close parentheses. Parentheses, and it says x is less than -3. So x second math less than -3. Second piece, parentheses 3x minus 1. Close those parentheses. And now here's how we've got to think about this inequality. This inequality is a compound inequality. It says that -3 is less than or equal to x, and x is less than or equal to 2. So it's two different inequalities separate. So we're going to type it in as two separate ones. So we're going to type in -3 second math less than or equal to, so 6, and then I'm going to put an x, and then I have to put the word and you can't just type it in. You got to go get it in the right spot. So here's how you get that. Second math, and then go to the right one, and there's the word and then x second math less than or equal to 2. I'm going to hit graph to make sure that works. Sometimes I can't remember whether I can type it in like that or not. I hope I can. Yeah, we can. All right, good deal. All right, so just split it apart, put and in the middle. Now we need that last piece, parentheses, -4x, close parentheses, and then x is greater than 2. X, second math, greater than 2. And then hit graph, and there we see all of the wonderful picture that we drew by hand with this calculator nicety out of that. So nothing really just fancy about that, but it does help us get the graph drawn anyway. All right, now we've already done domain, range, and continuity for that, so let's move on to not graphing these things and do some basic math with these. Function value. We did this in 100. Function value, if you had a function f of x is equal to 10x minus 9, and I ask you to find f of -3, what does that mean? Yeah, plug that in for x. F of -3 means 10 times -3 minus 9. And then work that out. So that's -30 minus 9, which is -39. So there we have. That's what function value tells you to do. The difference when we have piecewise defined functions is we have to check which piece do we even use. Because depending on what x is, which one of the pieces we use, because of those domain pieces that are out there, the inequalities that are out there, they tell us when x is a certain number, we use this piece. So let's look at example D, or C, excuse me. Example C, f of x, and then here's our piecewise defined function. X to the third power plus 2x squared minus 5. So something a little more fancy. If x is less than -6. And then 5x minus 8 if x is greater than or equal to -6. So we want to find, the first one we want to find is f of 10. So when we look at that, the part we're looking at is the 10. Where does 10 fit into those inequalities on the right? It fits in for x, but for which function does it work for? 10 is what kind of number compared to those inequalities? So the first inequality says less than -6. Is 10 less than -6? Definitely not. The second piece said x is greater than or equal to -6. And since 10 is going in the place of x, is 10 greater than or equal to -6? Definitely. So what that tells me is I need to use that piece of the piecewise function. is use the 5x minus 8. So when I do the work, I'm plugging in 5 times 10 minus 8. I don't worry at all about the top part. Okay? So that's going to be 50 minus 8, which is 42. So the final answer for that piece is 42. You use the one that the number fits into is the inequality. So 10, if you plug in 10 right here, is 10 less than negative 6? No, so I can't use that piece. I go here, is 10 greater than or equal to negative 6? Yes, so that's why I'm going to use that number, that piece, the 5x minus 8. Okay, let's look at part 2 there. F of negative 7. So we go to negative 7, we plug it in up here. Is negative 7 less than negative 6? Yes, so that means I've got to use that piece. So I'm going to plug negative 7 into that x cubed plus 2x squared minus 5. So negative 7 cubed plus 2 times negative 7 squared minus 5. I'm going to use a little help here. Parentheses, negative 7 raised to the third plus 2 parentheses, negative 7 squared minus 5. Just cranking that out. Negative 250. That's the y value that it goes with. Again, you don't pay attention to the second piece because that's not the one that x value matched up with. You have to check those x values in the inequalities. Let's do one more. And they always kind of try to throw this one at you because it's the tricky one. F of negative 6. Which one of those does negative 6 work in? Why the second one? Because it says equal to, and negative 6 is equal to negative 6. So I'm going to plug in 5 times negative 6 minus 8. That I can do. Negative 30 minus 8. Negative 38. So function value with piecewise defined functions, you've got to check your number that they're wanting you to put in for x in the inequalities before you plug it in. Find the one it works in. Use that piece. Don't worry about the rest of them. Okay? All right. Any questions about piecewise functions? That's pretty much what we're doing with them in this course. There aren't a whole lot of applications of piecewise defined functions in life. Pretty sure they're not going to ask you to do that at Food Giant. So if they do, y'all give me a call. I want to work at Food Giant. All right. Next section. So I'm going back to regular notebook paper for this one. This is in your book. Is section 2.8. Function operations. Operations. And compositions. All right. So when we're doing function operations and things, again, we're going to talk about domain along the way. And when we're finding domain of functions, we talk about, or I talked about in 100, these red flags that can happen. What are the 2 red flags that are things you look for when finding the domain of an equation or a function? If it's a list of ordered pairs, a repeating x value, that's true. What if it's an equation? What are the 2 things that cause problems with equations as far as that goes? But that's right, absolutely. I wasn't even thinking about a list of ordered pairs. That's true. X is repeating on a list of ordered pairs is not a function. What do we look for when we're looking at domain or an equation? Does anybody remember? Division by a variable. If that's happening, then we've got to figure out what would cause division by 0. Remember setting the denominator equal to 0 to find the domain of that. So that's going to be one of the red flags we look for. As we're looking at function operations and compositions, we've got to find the domain of the composite function or the operated function. So we need to look for the division by a variable so that we can eliminate the x values that would cause division by 0. And the other one was square roots. All right, so in the division by 0, we're looking for things that are going to make it divide by 0. When the square roots, we're looking for greater than or equal to 0, because if we take the square root of a negative number, what comes into play? Imaginary numbers. And when we're talking about domain for functions, we're only talking about the real number system. So we don't want complex numbers or imaginary numbers in there. So when we're finding domain, if there's a square root with a variable inside, we got to find out when is that greater than or equal to 0 so that we can talk about that as the domain. So let's do a couple of domain problems real quick just to review that idea. And all we're doing here is find the domain. So example A, f of x is equal to the square root of 8 minus 2x, something like that. All right, so there we have a square root with a variable inside of it. So to find the domain of that, we just set the stuff that's inside of the square root greater than or equal to 0. And we're going to solve that to find the domain. So subtract 8. Greater than or equal to negative 8. And then divide by negative 2. What happens when you divide by a negative with inequalities? Yeah, it flips that sign around. So it's x is less than or equal to positive 4. So our domain if we did set notation, it'd be all x's such that x is less than or equal to 4. But we do interval notation in here. So the interval notation for that would be negative infinity to 4 with a bracket. Same rules. We're finding the domain. Let's say we had g of x is equal to x squared minus 8 over x minus 9. Something like that. There is a division by a variable. That x minus 9 is in the denominator because that has a variable in it. Then we've got to figure out, okay, what x value could make that equal 0. So we take that denominator, x minus 9, and set it equal to 0 and solve it. That's an easy one. You just add 9. And if x were 9, then we'd get division by 0. So the domain in set notation is all x's as long as x does not equal 9. In interval notation, we go from negative infinity up to 9, skip 9, and then go to positive infinity. Been a minute probably since we've done that. Nobody probably practiced that over Christmas break. So just want to review that as we go along here. So that's going to happen quite often when we do division with functions, with the operations. So we're going to do addition, subtraction, multiplication, division. Division, you're going to have that come up every time. Very few times that won't come up. One last one. Let's say we had f of x is equal to x to the third power minus 7x squared plus 5x minus 10. Does that have either of the red flags in it? No. So what's the domain? All real numbers is what that means. You may have written it out like that last semester. I don't know. Negative infinity to positive infinity is the interval for that. Because it has no red flags, that's going to happen quite often in this section. But you're not going to have either of the red flags to deal with. So the domain is going to automatically be all real numbers or negative infinity to positive infinity. Okay. So those red flags, we've got to just keep an eye out for them. They don't happen on every problem. They're only going to happen on a few. So just be careful of that. All right. So let's do some function operations. We'll start with that. And then we'll get to, so with function operations, f plus g of x, all that means is you take the f of x function and add the g of x function to it. It's just addition. And when you add things together, you put like terms together. Subtraction, it's the same idea. F minus g of x just means take the f of x function and subtract the entire g of x function from it. When they're written like that, that means multiplication. So you're just taking the f of x function times the g of x function. You're just multiplying it out. It's usually going to involve some distributive property or some FOIL method or something like that. It's going to be involved there. So multiplying, and then the last notation there is the division. And that just means whichever one is listed on top, that's the function that goes on the top. The function that goes on the bottom is on the bottom. So you take the two functions and you divide them. Usually that you just stack them up in a fraction and that's all you do. And then you find the domain out of that. So we're going to look at a couple of different functions here and do all four of these operations with it. Okay. So here's f of x, x squared plus 5x minus 3. And then g of x is negative 3x plus 4. Those are the two functions we're going to do every one of these problems with. Okay, so example D is f plus g of x. So we're going to take the f of x function, x squared plus 5x minus 3, plus the g of x functions, negative 3x plus 4. What are the like terms? Was there anything like x squared? Nope. I'm going to put x squared down there. 5x is like what? Negative 3x. So what's 5x plus negative 3x? Plus 2x, right? And then we got negative 3 plus 4. Plus 1. There is our operated function, or the addition of those two functions. What's the domain of that? All real numbers, negative infinity to positive infinity. It doesn't have any of the red flags, so that's why it's all real numbers. Doesn't have a square root in it, doesn't even have a fraction in it, so we can't have the division by a variable. Okay? Easy enough. Same two functions. Let's do E. F minus G of X. Got to be a little bit more careful when you do the subtraction. So we're taking x squared plus 5x minus 3 minus negative 3x plus 4. Now, he put parentheses in there this time, and he didn't last time. Why did he do that? Well, it'll still make 3x a positive. but it would, if I didn't put the parentheses, it would have left 4 a positive. If we're subtracting the entire function, we need to subtract the negative 3x and subtract the 4. So this is like plus 3x minus 4. If you distribute that minus sign to that, that's what happens there. And then we put like terms together, the same way we did in example D. So that would be x squared plus 8x minus 7. It's the domain of that. Have any red flags? Nope, no square roots, no fractions, so it's all real numbers. Okay. Example F. Same two functions. We're going to multiply them together. Good old distributive properties, all this is. So I'm going to distribute x squared to both of those terms. So that's going to be negative 3x cubed plus 4x squared. Then I'm going to distribute 5x to both of those. So that'd be negative 15x squared plus 20x. Then I'm going to distribute the negative 3 to both of those things. So that'd be positive 9x minus 12. Once I've done all the multiplying, I'm going to put the like terms together. So we got negative 3x cubed minus 11x squared plus 29x minus 12. Okay. What's the domain of that? All real numbers again. No red flags on this so far. And a lot of that just depends on the original two functions that you get. Okay, for addition, subtraction, and multiplication, the original two functions you get are going to decide what your domain is. If they don't have any restrictions on them, your operated function is not going to have any restrictions on them. But when you get to the next example G, we're on, yeah. F divided by G of X. So there we're taking X squared plus 5X minus 3 divided by negative 3X plus 4. I'm not looking for you to simplify that right now. We'll do that in a couple of weeks. We'll do simplifying rational expressions and things. So don't worry about that right now. Main idea here is you've got the division written. Let's find the domain. How do you find the domain of that problem? Yeah, that's right. Take the bottom, negative 3x plus 4, set it up equal to 0, and solve it. Minus 4. And divide by negative 3. Last one. 4/3. So the only x value that we can't have is 4/3. So that's the set notation for that. The interval notation would be from negative infinity to 4/3, parentheses, parentheses, 4/3 to infinity. So there's the function and then the domain there. Anytime you do division of functions, your domain's going to have some restrictions on it. Part of the course. Okay. Let's get a couple of different functions and do the the domain for those, just to show that it could cause some issues there. So let's say we did h of x is equal to the square root of 2x minus 1, and then k of x is equal to 8x minus 9. And they ask us to find h plus k of x. These tend to cause some issues in this course sometimes, just because we don't know exactly what we're allowed to do and what we're not when we're adding and subtracting. So if we're going to add these two together, we're taking the square root of 2x minus 1 plus 8x minus 9. Here's the beautiful thing. There isn't anything you can do to that, because things that are under a square root are stuck there unless you can simplify it, and that's not going to happen on that. Right? So they're not like terms. So there's nothing you can do. So that's your function. And to find the domain, which part of that has a red flag? The square root part. The 8x minus 9 really doesn't do anything to it. The only red flag is the square root part. So we're going to set 2x minus 1 greater than or equal to 0 and solve that. Plus 1. 2x is greater than or equal to 1. Divide by 2. X has got to be greater than or equal to 1/2. So in interval notation, that would be bracket 1/2 to infinity for the domain on that. So restriction on the original function is going to equal a restriction on the domain of the operated function always. I mean, it's just the way it is. I'm going to show you an exceptional one, and then we'll move on to the composition of functions. Is k divided by h of x. So this one is a little weird, because k divided by h would put the 8x minus 9 where? Top. And the square root of 2x minus 1 in the bottom. And again, I told you you're not going to worry about simplifying this stuff until a couple of weeks from now, about 3 weeks from now. So it's, or maybe 4 weeks. I got to look at my schedule again. But nothing you can do to simplify that. But when you're looking at that, this one has a double red flag on it. Not only does it have a square root with an x inside of it, it's that stuff is in the denominator. So when you go to set up the domain for that one, you're going to set 2x minus 1. We normally, because it's under a square root, would set it greater than or equal to 0. But because it's in the denominator, can it ever equal 0? No, because what's the only number in the world we can't divide by? 0. So we have to take the equal to part off of that. And we solve 2x minus 1 is greater than 0, which we've already done that math. So we know that x has got to be greater than 1/2. So our domain is, instead of a bracket, it's going to be parentheses 1/2 to infinity. Yes, ma'am. Why did we use greater than or equal to on the first one, but we're not using it? Because the first one, the square root was not in the denominator. We're not, the equal to goes away because we cannot divide by 0. So if we had included the 0 here, that would have been division by 0, and we can't do that. That's an undefined operation out of that. Any other questions about operations or anything with the domains that we're doing here? All right, so last thing in this section is the composition of functions. So function composition. And function composition has a little notation. It looks like the word fog, but that's just a small circle there. It's not the letter O. It's not a dot. It's a small little empty circle is what's in between the two letters there. So F composed with G of X is what that's how you read that. So we'll write that. F composed with G of X. That's the way that that's read. F composed with G of X. The way that it works is it's like function value. You take the second function that's listed in the composition statement and you put it inside of the first function. So it's F of G of X is the math that's going to happen, and I'll show you that in just a second. All right. So let's get a couple of pretty not so scary functions to deal with here. So let's go. F of X is equal to 2x plus 5, and G of X is equal to negative 8x minus 1. Something very, very simple to start off with, and then we'll get a couple of more difficult functions to do some composition with. All right. So let's do F composed with G of X. And I don't know what letter we're on here. I lost H-I-J. So I'll have to do that too, where you have to tell yourself what the alphabet is. F composed with G of X. And then we're also going to state the domain once we get done with that. All right, so we're taking G of X and putting it inside in the place of X in the F function. That's what the math of a composition does. So we're taking this problem and put it into place of X in that problem. That's what we're doing. Okay. So that's going to be 2 parentheses negative 8x minus 1 plus 5. All we got to do now is simplify it. Okay. So how do we simplify that? Yeah, distribute 2. So that's negative 16x minus 2 plus 5. One more step. Negative 16x plus 3. That is our composite function, F composed with G of X. What's the domain of that composite function? Are there any red flags? Yes, no, maybe. No red flags, no square roots, no x's in the bottom, so we're good. That's all real numbers. So negative infinity, positive infinity. There's our domain out of that. Pretty simple functions to deal with there, but they're going to get tougher, but just bear with me. Let's do one more with those easy ones. Let's do G composed with F of X. So that means we're taking the F of X function and putting it in for X in the G of X function. So we're taking those two functions up here and we're taking this guy and putting it in the place of X right there. That's what that means. Okay. That's going to be, excuse me, negative 8 parentheses 2x plus 5 minus 1. Again, distribute minus 40 minus 1 negative 16x minus 41 is that composite function. Again, no restrictions, no red flags happening there. So negative infinity, positive infinity for the domain. Okay. Easy stuff when it's easy functions. Let's get a little more difficult here. Let's take f of x as, let's do that 2x minus 1. And then let's take g of x and do 4 over x minus 1. Okay. And what are we on? Okay. F. Let's do f composed with g of x. These. So take in g of x and put it in the place of x in f of x. So that's going to be 2 parentheses, big fraction, that looks super complicated or it looks harder, but it's not. How do you multiply by 2 to that fraction? You multiply the top, the bottom, or both? Both of them get multiplied by 2? This is yes. This is no. Now, how do you multiply fractions? Straight across. 2 times 4 is 8. 1 times x minus 1 is x minus 1. And then minus 1. There's our composite function. We're not going to. In about a month, we're going to be doing a little bit more with that. But right now, that's our composite function. Now, it's the domain of that. What's the red flag that shows up? The fraction with the x in the denominator. So how do I take care of the domain for that? Set x minus 1 equal to 0. So x cannot be positive 1. So my domain is from negative infinity up to 1. Skip the 1. And then go on to positive infinity. Okay. Not too bad. Just looks a little tough because it's got the fraction in it. Okay. Still not that hard stuff. Just don't overthink it. Don't get psyched out by it. That's what usually happens in this section. All right. Let's do g composed with f for these same 2 functions. And then we'll do one more set of functions here. So we're taking the first fraction or first function, 2x minus 1, and putting it in the place of x in the second function. So it's going to be a big fraction, 4 over 2x minus 1 minus 1. So this part was the f of x. So we just replaced that x with the f of x. That's where that came from. Now I can simplify the denominator a little bit there, right? Because I got like terms. We got the minus 1 and the minus 1. So that's going to be 4 over 2x minus 2. And then in about a month, we're going to do a little bit more with that to simplify it. But right now, that's enough. And that's our composite function. The domain, again, what's the red flag that comes up? The x in the denominator, right? Set that equal to 0 and solve it. So x can't be 1. Again. Won't always be the same number. It'll change from time to time depending on the functions. The process is the same though. Let's do one more set of functions. Let's say we had h of x is equal to the square root of x. Real simple. K of x is equal to 4x plus 2. Also pretty simple, but both with their own, one with a very interesting set of domain there. So let's do example n. Let's do h composed with k of x and find the domain. So what am I doing? That's right. Put 4x plus 2 underneath the square root. Good job. That's it. That's our composite function. That was pretty easy. Now, how do we find the domain? Close. That's part of it. That's the other part of it. Both. It's greater than or equal to 0. And then solve that. Minus 2. 4x greater than or equal to negative 2. Divide by 4. X is greater than or equal to negative 1/2. So our domain is from negative 1/2 to infinity. And there's our composite function there. All right, last one for this section. Let's do a function value from a composite function. So sometimes they can ask you to do a function operation and then put a number in that. So if they ask us to do h composed with k of x, or instead of x, they put the number 3 in there. Well, what do we know about h composed with k already? That it is the square root of 4x plus 2. What does that 3 right there, where does it go? In the place of x. That's all that means. Do the composite function and then put the number in there. So that's going to be the square root of 12 plus 2, which is the square root of 14, and that doesn't simplify any. So that's all you got to do. So they can give you function values mixed in with addition, subtraction, multiplication, division. You just do the operation or composition first, and then plug the number into x after you get done with that. So it's really just the easiest, probably the easiest part is the last part, but the operation is the harder part. All right. I don't think we're going to make my 7:15 plan, but we got one more section to do here. So
was that last one, would you find the domain, or
no, because you're just finding the function value, so you're not really looking for the domain there. You're just finding the y value that goes with that x is all you're trying to do there. Okay. All right. Let's see. All right. Let's just push through and do this section that way. Because I'm afraid we'll get behind and it'll snow and we'll miss a week or something like that. So I don't want to do that. So, all right, going to chapter 4. So this first night kind of skips around chapters and stuff. After the first couple of weeks, it settles down into doing like a chapter at a time, or at least everything is very much related. So this one is going to be inverse functions. All right. One thing to know is not every function has an inverse function. Okay. 1-to-1 functions have inverse functions. 1-to-1 functions means, the rule for functions is that x's can't repeat. To be a 1-to-1 function, x's can't repeat and y's can't repeat. Neither. That's a 1-to-1 function. So not every function is 1-to-1. Not every function has an inverse function. Doesn't mean it doesn't have an inverse, just doesn't necessarily mean that inverse is a function. So 1-to-1 functions have inverse functions. There's a quick test for 1-to-1, ness of a function. The 1-to-1ness of a function is tested using the horizontal line test. All right. Remember the vertical line test to decide if a graph was a function or not? We used in 100, where you look at a graph. Let's say, for example, I'm going to sketch one here. Doesn't have to be precise or anything. Just there's a coordinate plane. Here's a graph. There's a nice parabola. That passes the vertical line test because no matter where I put that vertical line, it only hits that blue line once, right? So that passes the vertical line test. But if I try the horizontal line test, it's the same rules. If I drop a horizontal line anywhere on that graph and it hits it twice, it fails. What that shows is that those two places where this line hits, different x values, but the exact same y value. So that shows that this is not 1-to-1. So not 1-to-1. A 1-to-1 function, one of the easiest ones to draw, is just a straight line, like a linear equation. Something like this. Straight line like that. That passes the vertical line test. No matter where I put a vertical line, it only touches it once. And then it passes the horizontal line test. No matter where I put a horizontal line, it only touches once. So that is a 1-to-1 function. Okay. So horizontal line tests can decide if a function is 1-to-1 or not. And the best thing to do is just look at the graph. Okay. Don't try to pick x values and all that jazz that could come along with this. Just graph it and look at the graph. So let's look at a couple of functions real quick and decide, are they 1-to-1? Are these 1-to-1? Example A. F of x is equal to -4x plus 12. I'm not going to think about it too hard. I'm just going to go to my calculator. I'm going to clear out all these equations that I typed in earlier, and I'm just going to graph -4x plus 12. Does that pass the horizontal line test? Yes. So it's 1-to-1. B. G of x equals square root 25 minus x squared. Okay, a little tougher to graph that one, but it's still doable. I'm just going to go to my graphing calculator and hit y equals. We'll get a square root symbol. Oops, button. Y equals square root symbol, second x squared, 25 minus x squared. Would that pass the horizontal line test? Definitely not. No, that is not a 1-to-1 function. There's not. So horizontal line test, easiest way to tell if something has an inverse function is, does it pass the horizontal line test? So if you got an equation, that's the way you're going to test it. Okay. All right. Let's talk about inverse functions. Inverse functions swap x and y. Remember, x is the domain and y is the range. Technically, the wording should be that they swap the domain and range. We know that that's just x and y. So if we're talking about a set of ordered pairs and they ask for the inverse, just turn the ordered pairs around. X and y swap. That's all you got to do. Okay. So inverse functions swap x and y, swap the domain and range. That's what they do. Okay. Now, with inverse functions, when we talk about equations, we can prove or disprove that functions are inverses of one another using function composition. So this is where that stuff that we just talked about has some sort of application here. It's probably not a life application to this, but it's Math 110 application to it. So if f of x and g of x are inverse functions, then f composed with g of x equals x, and g composed with f of x equals x. What that says is that if you do the function composition, you're going to get plain x back. Nothing different. Not a negative sign on that x, not that x in the denominator, not x plus 2, not x times 7, just plain x. If you do the composition with the two functions and you get x back, then they're inverses of one another. That's what that says, okay? So that's one of the things that we can use to test if two functions are inverses of one another. All right, so we're going to test to see if two functions are inverses of one another. Example C. R f of x equals 8x plus 5 and g of x equals 1/8 x minus 5/8 inverse functions. We're going to do that composition. So we're going to do f composed with g of x. Okay. So what does that mean to do? How do we do that composition? Take g and put it in the x for f. That's exactly right. So I'm taking 8 parentheses 1/8 x minus 5/8 and then plus 5 on the outside. So I'm just replacing the x in the f of x function with whatever g of x was. And then I'm going to simplify that. So I would distribute this 8 to both of those terms. So that'd be x minus 5. And then since I've distributed, I don't need the parentheses anymore, so I'm not going to write them. And then plus 5. What is negative 5 plus 5? 0. They cancel each other out, right? So that's just plain x. What does that tell me? They are inverses of one another. Technically, if you were going to prove that two functions are inverses of one another, you would need to show that g composed with f of x is equal to x. You would need to show that. I'm not requiring you to show both ways out of this. If it works one direction, then it will work the other direction as well. But mathematically, if you're going to prove it, you got to show both ways. One way is good enough for me. Okay, in Math 110. Most of us are not going on to be math majors and need to write a bunch of mathematical proofs along the way here. But if you did need to prove it, you would have to show both ways. Okay, so one direction is good enough out of that. All right, so function composition. Now here's another neat thing that happens with functions that are inverses of one another. I'm going to graph each of those on my graphing calculator. So I'm going to graph 8x plus 5, 8x plus 5. And then I'm going to graph 1/8, 1 over 8, x minus 5 over 8. And then I'm going to graph a third line. I'm going to graph that plane X that I got when I did those compositions. Okay. Here's what happens. When I graph those three and I look at my graph, this line and this line are the two functions. This one that's coming through the middle there is the X. They reflect across the Y equals X line. Okay. Notice how if you folded this screen along this line that's going through the middle, that this side would match up to that side. And the same thing is happening here. Inverse functions reflect across the Y equals X line. So sometimes you can tell by graphing. Graphing is probably not the best way because especially when you get functions that get further and further apart and you only see part of the graph on your screen, it doesn't look, it's real hard to tell. But that is another way of telling if two functions are inverse to one another, if the graphs reflect across the Y equals X line. Not the best way, but it is a way. And if you don't have if you're having trouble doing the composition, maybe that's an option for you to be able to check and see if two functions are inverse of one another. Okay. So reflecting across the Y equals X line is what inverse functions also do. Okay. So that's important to know how to determine if two functions are inverses. Composition has got to be equal to what? X. If you graph it, what do they reflect across? Y equals X, the X line, okay? All right, so now let's do the actual taking a function and finding the inverse of it, okay? So we'll do 3 or 4 of these, and then we'll get into the, then that'll be it. All right, so what letter are we on here? D. All right, I'm trying to cut a little out for you. 3x minus 7, and we're going to find the inverse. Find the inverse. I know that is a one-to-one function because it's linear. It's 3x minus 7. If I graph that, that passes the horizontal line test. So that's how you know that you can find the inverse function. Now, what did we say that inverses do? Earlier in this section. They swap x and y. So what we're going to do is we're going to take this equation, and f of x is the same thing as y, right? That's just another way to write that equation. Instead of f of x, we can write it with a y in it. Inverses swap x and y. So we're going to swap x and y. And I'm just writing the steps that we're going to use here. So I'm going to have x equals 3y minus 7. The next thing that I'm going to do is I'm going to take that new equation and solve for y. So I've got x equals 3y minus 7. To get y by itself, I would add 7. So that'd be x plus 7 is equal to 3y. And then I'm going to do what? Divide everybody by 3. And I'm going to divide them individually like that. And I'm going to write it as 1/3 x plus 7 over 3 is equal to y. Once I get y by itself, that's the inverse function. So the inverse function in function notation, that's the last thing. The function notation for inverse is f, or whatever letter that they named the function. This was f of x to begin with, and then put a little -1 exponent on that. F, and the way that's read is f inverse of x is equal to 1/3 x plus 7 over 3. So swap x and y, solve for y again. Then once you get there, change it to the function notation, and that's the inverse function. if I graph the original problem and this one, they're gonna cross the x-axis, or they're gonna reflect across the y equals x line. If I did the function composition with this answer and the original problem, I'm gonna get plain x back, because they're inverse functions of one another, okay? So, function inverses are easy to find, sometimes, not always, but sometimes they're easier to find. So let's do another one. Let's take example E here. G of x is equal to 2/3 x plus 5. Again, just going to take a linear one to start with here, and then we'll build up from there. And see if we can get the inverse of that. So first step to finding the inverse is swap x and y. And then solve it for y again. So what's our first step? Minus 5. So x minus 5 is equal to 2/3 y. The last step. Divide by 2/3, which is also the same thing as multiplying by the reciprocal of that, 3/2. Anytime it's fractions, I always just do that way. And then distribute that 3/2. So that's 3/2x minus 15/2. And then we're going to write it in function notation. G inverse of x equal to 3/2x minus 15/2. Okay. So easy when it's a linear piece, linear function to start with. That's not too difficult. Let's get a little bit more difficult. Let's say we had f of x is equal to x squared plus 2. And then they say this little thing here on the outside, they say x is greater than or equal to 0. What that does, when they put that little domain thing out here on the side, is it makes this a one-to-one function. If I had graphed x squared plus 2 with the whole domain of all real numbers, then it creates a parabola, which does not pass the horizontal line test. X squared, you remember x squared graphs make parabolas, and they don't pass the horizontal line test. When they do this, what that does is it makes it be a one-to-one function that will pass the horizontal line test, which means then, hey, you can find the inverse function of that. So, so let's find the inverse of that. Again, first step, swap x and y. So that's going to be x equals y squared plus 2. And now what? Subtract 2. X minus 2 is equal to y squared. And how do you undo squaring? Yeah. So I'm going to take the square root of both sides. And technically, there's a plus or minus when I do that. But which one of those am I going to use? The positive side or the negative side? Because I can't use both. Why the positive side? That's right, but why?
Because it's got to be greater than 0.
Why? Where did you get that from?
The domain.
Very good. The domain on the top said x is got to be greater than or equal to 0. What kind of numbers are greater than or equal to 0? Positive ones, right? So if it had said less than or equal to 0, we'd have used the minus side of the plus or minus on the square root. Okay. So the domain at the beginning tells you which side to use, positive or negative. Since it's greater than, positive side. If it was less than, negative side. Okay. So that makes that a little easier to understand. So function inverse notation there. Inverse f inverse of x would be positive square root of x minus 2. There's the inverse of that one. Okay, so a little bit more difficult there. Now let's do the hard one, or a couple of the hard ones. Excuse me. All right, so we got f of x is equal to 2x plus 3 over x minus 4. And the domain that they have to tell us, x doesn't equal 4. That doesn't necessarily make this 1-to-1, but that's just the domain for that problem. And they will usually, your textbook, and the Canvas quizzes and stuff will usually just add that to it, just so that you know out of that. So this is a 1-to-1 function. Go ahead and tell you if you graph that, if you graph the calculator, it does pass the horizontal and vertical line test. So we're going to find the inverse function for this. So this is a little bit more difficult because it has x's on the numerator and the denominator. So when you swap x and y, you're swapping both of those. So it's going to be x equals 2y plus 3 over y minus 4. Which makes this a little bit more difficult to solve because now you got y in two different places. And right now the y is in the denominator, so I need to get it out of the denominator. So the only way to do that is to multiply by whatever that denominator was, which is y minus 4. So I'm going to get 2y plus 3 on the right side. And on the left side, I'm going to distribute that x. So I get xy minus 4x. And this one looks a little tricky because you got an x and a y that are tied together with multiplication, and then on the other side you got something else with a y. So if we're trying to get y by itself, we need everybody that's got a y to be on the same side, right? And everything that doesn't have a y to be on the other side. So I'm going to move the 4x by addition over here. So that gets me xy is equal to 2y plus 4x plus 3. And then I'm going to move the 2y by subtraction. And if you want to do that in one step, that's absolutely fine with me. I just want to show it in extra one piece at a time there. So xy minus 2y is equal to 4x plus 3. Now I have everybody that's got a y is over here. Everybody that doesn't have a y is over here. We've got to think about one of our skills that we learned or worked on in Math 100. What do we see happening over here? Or what could happen? Or what do they have that's the same? They both got a y. So in 100, we did a lot of what? With F, you did with factoring. Factoring, all right? So they have a common factor, right? What is the common factor for both of these pieces? Y. All right, so if I factor a y out of that, it's going to be one step closer to getting it done. We're almost done. We're one step away now. What's going on between y and this parenthesis here? What operation? And what math do we do when we distribute? We multiply. So this is really y times this stuff. So the inverse of multiplication, or the opposite of multiplication, is division. I want to leave y by there, right? So I need to divide by the other stuff. The other stuff is x minus 2. So I'm going to divide both sides by x minus 2. And there I finally have y by itself again. I'm going to get 4x plus 3 over x minus 2. And then I'm just going to rewrite it in function notation. F inverse of x is equal to 4x plus 3 over x minus 2. And there I found the inverse function out of that. A wee bit harder than the other ones that we've done. Okay, these are the hardest ones that they do. That's why I do a couple of these with you to make sure that we have seen some of it, and you've got some examples to go back to. This doesn't come up every problem by no means, but it's going to be on there. I've seen it on the final almost every year, so that's why I spend a little extra time on it. One more of those. Let's do this one. See if we can knock it out. H. G of x is equal to 3x minus 8 over x minus 5. And again, they're going to tell you x does not equal 5. But that doesn't matter. It's not going to make any difference in this problem. Okay, so we're going to set that up and find the inverse of that function. Okay, so first thing we do is what? Swap x and y. So that's easily done. 3y minus 8 over y minus 5. What's the next step? Multiply by y minus 5. Good job. And as you've done, if you do a bunch of these, you'll start seeing a few shortcuts that you can take. As far as I know, hey, this is going to happen here, and I see that happen. Because they're not going to get too crazy with the numerator and the denominator. They're not going to make those very big. Now what? All right, so get all the y's on the same side and all the stuff that ain't y's on the other side. Okay, so add 5x, and I'm going to subtract 3y at the same time. The xy minus 3y is equal to 5x minus 8. And if you wrote that in a different order, technically it's okay. But generally, the accepted way of doing things is the variable part first. But it's technically the same. All right. So what do I do after that? This is the clever step. GCF y x minus 3. Last step. Divide by that x minus 3. 5x minus 8, x minus 3, and put it in function notation. G inverse of x equals 5x minus 8 over x minus 3. I do think I did use G. Yeah, I did use G. Okay. Once you've done a few of them, it's not too bad. You just got to see that trick to do that. One last problem, and we're out of here. It's the last one of the night, and it's a little easier. It won't take us very long. So f of x is square root of x plus 5. And the domain of that would be, we know x has got to be greater than or equal to negative 5. Let's find the inverse of that. So this one starts with a square root in it. This is why this one's a little different, but it's not hard. What's the first thing we do? Swap x and y. So x equals the square root of y plus 5. Now what? Square the x, and if I square the left side with the x, I got to square the right side. But what happens on the right-hand side? You lose the square root. That's all that happens over there. And the left-hand side, you just got x squared. Good job. One last step here. Subtract 5 minus 5, yeah. So x squared minus 5 is equal to f inverse of x. It really is that just getting rid of the square root, just knowing that you square both sides is all you've got to know there. Not fancy, nothing to that. All right. Now, as I said, I always list out some potential practice problems for each section that you're welcome to look at. And if you will do those, that will prepare you for the Canvas quizzes. I always just say odd, just because the answers are in the back of your book. And by no means do I mean you have to do all of these to be prepared. Just some of each kind can help you get ready for that Canvas quiz. Canvas